Have you ever, looked at a massive report, maybe an entire book, or just like a huge pile of notes or some complex project and just thought, how am I ever going to get through all of this? And more importantly, how do I make sense of it, without getting totally swamped and losing those crucial little details? Well, imagine an AI facing that exact same problem. Because for large language models, LLMs, there's this huge hurdle. It's called the context window problem. Basically, current LLMs really struggle to process what we might call infinitely long documents. They can't do it efficiently, and their performance really starts to degrade. It's kind of like trying to remember every single word from, I don't know, 1,000 books all at once. It just doesn't work well. But what if? What if an LLM could tackle a huge research task in a way that actually mimics how you might do it, by intelligently sifting, summarizing, focusing only on what's really important? Today, we're going to dive deep into a really groundbreaking new approach. It lets LLMs handle truly massive amounts of text. We're talking millions of tokens. And it does it by, well, acting a bit more like us.
Yeah, and what's truly fascinating here, I think, is that this isn't just, a small step forward. It really addresses a critical bottleneck in AI right now. We're unpacking a paper called MemAgent, Reshaping Long Context LLM with Multi-Conv RL-based memory agent. It's from researchers at ByteDance Seed and also the Institute for AI Industry Research, AR, at Tsinghua University. Pretty recent, too, published July 4, 2025. And this work, it really aims to fundamentally change how LLMs handle huge amounts of information, basically giving them a kind of human-like ability to take notes as they go.
Okay, so let's unpack that bottleneck. Why exactly is handling these really long contexts so hard for LLMs? I've heard this term thrown around, O(n)2 computational complexity. Can you break down what that actually means for performance, like in simple terms?
Yeah, absolutely. Think of it like this. If you double the amount of text an LLM needs to process, the computational effort, it doesn't just double, it can actually quadruple, or sometimes even worse. The processing time just, well, it explodes as the text gets longer. That O(n)2 complexity, it's a real fundamental hurdle. And if we look at how people have tried to solve this, well, current approaches trying to extend these context windows, they each have pretty significant limitations. There are generally sort of three main schools of thought, you could say. First, you've got length extrapolation methods. These try to make the model understand longer sequences by tweaking things, like positional embeddings. Now, they're promising in theory, but they often suffer from, real performance degradation and slow processing speeds, because they still ultimately run into that O(n)2 computational complexity problem, especially with really enormous texts.
Right, so stretching the existing model only gets you so far before it breaks down or it gets too slow. Okay, what else?
Then you have approaches like sparse or linear attention. These try to reduce that complexity basically by having the model pay attention to fewer parts of the text at once.
Okay, that sounds more efficient.
It can be, but the issue here is that these often require training a whole new model pretty much from scratch, which is incredibly expensive, time-consuming, and they can run into other difficulties too, like linear attention sometimes struggles with parallel training, or sparse attention might need humans to define the patterns. It's not usually a simple plug-and-play solution you can just add to existing models easily.
Gotcha. So more efficient, but harder to implement and maybe less flexible. What's the third way?
And finally, there are context compression methods. These use things like, say, token-level compression or maybe external memory modules to try and condense the information before the main LLM sees it. But while they do make the input shorter, they typically struggle with what's called extrapolation, performing well on texts much longer than what they were specifically trained on. And, crucially, they inevitably kind of mess with the LLM's standard generation process. That can hurt compatibility with existing systems and often makes parallel processing difficult. They fundamentally change how the LLM operates, which isn't always ideal if you want to adapt current models.
Okay, so putting all that together, it sounds like for a really successful long context LLM, we're chasing this kind of trinity of requirements, right? It needs to handle basically infinite length text. Or practically infinite.
Right.
It needs to maintain its performance, not get dumber as the text grows.
Lossless extrapolation is the goal.
And it needs to do all this efficiently with processing that scales ideally, linearly, not quadratically. That's a really tall order. Which of those three do you think was maybe the toughest nut for MemAgent to crack?
Oh, that's a great question. I mean, they're all challenging, definitely. But I'd say achieving that near lossless extrapolation, maintaining performance without a significant drop across vastly different lengths, that's particularly tricky. Models naturally tend to perform best on the kind of data lengths they were trained on. Getting them to generalize so well is tough. But MemAgent's solution here is, I think, quite elegant.
Okay, so this is where MemAgent gets really interesting, taking that page right out of your book, the listener's book, right? Think about how you would tackle a massive document, like a really dense research paper. You don't try to memorize every single word, do you? No way. You probably skim, you abstract the main ideas, maybe jot down some notes, and you consciously, actively discard irrelevant information. That's selective attention in action. It's a very human skill.
Precisely. And MemAgent adopts what the paper calls this anthropocentric intuition. It's deeply inspired by how we humans manage large amounts of information, and it manages this by using a dynamically updated, but importantly, fixed-length memory. The model doesn't just try to cram everything into an ever-expanding window. Instead, it intelligently summarizes and decides what's crucial to keep.
Okay, so how does that work in practice, like step by step?
Yeah, the workflow is quite clever. MemAgent processes the text segment by segment, like reading chapter by chapter almost. And as it reads each segment, the model proactively and selectively updates its internal memory. It uses what they call an overwrite strategy. So it might replace older, less relevant info with newer, more important stuff.
And this memory, it's not some weird external database.
No, and this is crucial. This memory is just a sequence of ordinary tokens that live inside the model's standard context window, which means the core LLM generation process, the way the model actually thinks and writes, remains totally unchanged. That maintains compatibility.
Ah, clever. So it didn't break existing LLMs.
Exactly. The system essentially has two main parts, or modules. There's a context processing module that iterates through the document chunks and updates that memory. And then there's an answer generation module that looks at the original question or task and consults that condensed memory to produce the final output.
Okay, and the benefits of this approach.
This design yields three really key benefits, which the paper highlights, and they directly address that trinity we talked about. First, unlimited length, essentially. The document can be millions of tokens long because it's just processed as a stream. The model only ever sees a fixed size window plus its memory.
Wow, okay.
Second, no performance cliff. Because it's actively deciding what's important using this memory, it avoids that sharp drop in accuracy you see with other methods. They call it near lossless extrapolation.
That's huge.
And third, linear cost. Because the memory size and the processing window are constant, the decoding time and the memory the computer needs only grow linearly with the input length.
Yep.
ON, not ON2. Super efficient.
Right, so it scales beautifully. Okay, but how? How does MemAgent get so smart about what to remember and what to forget? What's the secret sauce for telling important bits from digital fluff? This is where that reinforcement learning, the RL, comes in, isn't it?
That's absolutely right. RL is essential here. And the reason is, well, these memory tokens, they're kind of like hidden states inside the model. They're latent variables. And they're updated using this very specific, discrete step-by-step rule that overrate thing. Traditional training methods, like just back propagation, they can't directly optimize for what makes a good memory state through these discrete choices. You can't just, write a simple loss function for good remembering.
Okay, so you need a different way to teach it.
Exactly. So the training approach uses a specialized RL algorithm. It's called Multi-Conv DPO, which is an extension of some existing techniques. What it does is treat each segment processing step each time it reads a chunk and updates memory as a kind of mini context-independent conversation and an optimization target. Then, after processing the whole document, the model gets a final reward. This is based on whether it produced the correct answer to the overall question.
Ah, okay, so the reward comes at the very end.
Yes, but here's the clever bit. That single final reward signal is then uniformly applied or credited back across all those mini conversations, all those memory updates that happen for that one document sample. This bridges the gap. It connects getting the final answer right with all the implicit, intelligent decisions made along the way about what to keep in memory. It essentially learns through this feedback how to take good notes that lead to the right answer.
That is clever. So the reward isn't just for the final output, but it kind of flows back to reinforce how it built up that useful memory step by step.
Precisely. It reinforces the entire chain of good memory management decisions.
And what about looking inside? Can we actually see what the AI is choosing to remember? Is this memory a black box?
No, and that's another really cool aspect because MemAgent's summaries, its memory, they live in the normal token space. They're just text. So every intermediate memory state it creates is actually human readable. You or I could inspect it, see what it decided to keep. You could potentially even edit it.
Whoa.
It's almost like the AI is creating its own legible study notes as it processes the information, which is frankly, amazing for understanding what it's doing, for debugging.
Mm.
And yeah, it's a bit mind-bending to think about.
Okay, theory sounds fantastic. Human-like memory, RL training, readable notes.
Yeah.
But how does it actually perform? Does this human-inspired selective attention hold up under pressure in real-world tests?
Yeah, the results they reported are quite impressive. Let's look at the experimental setup first. They trained MemAgent on a relatively modest 8K context window. So that's the chunk size plus memory it sees at any one time.
Okay, 8K. That's not tiny, but it's much smaller than some recent models claim.
Right. And within that, it had a 1024 token memory and processed document chunks of about 5,000 tokens. It was trained on about 32,000 documents, synthesized from a dataset called Hotpot QA, which involves multi-hop reasoning. Then they tested it. On question answering tasks, they pushed it up to an astounding 3.5 million tokens of input context.
3.5 million. Seriously.
Seriously. And they also evaluated it on what are called out of distribution, or ODE, tasks from a benchmark called Ruler. This includes things like the needle in a haystack tests, finding a specific piece of info in a huge document, plus variable tracking, finding frequent words. And they tested these up to 512,000 tokens.
Okay, so really pushing the limits.
Yep.
And the results. Don't leave us hanging.
The main result is genuinely striking. MemAgent showed, and I quote, superb long context capabilities. It was able to extrapolate from that 8K training context all the way up to a 3.5 million token QA task with a performance loss of less than 5%.
Less than 5% drop going from 8K training to 3.5M testing. It's incredible. Let that sink in. Trained on 8K, handles 3.5M almost perfectly.
It is, and it also scored over 95% accuracy in those 512K Ruler benchmark tests. Really solid across the board.
That is remarkable, especially that minimal accuracy loss. It avoids the cliff completely. But, how does this compare to other models designed for long context? Are they even in the same ballpark?
Well, that's where the contrast becomes really clear. The paper shows that baseline models, even really good ones designed for long context, they just fail to maintain consistent performance. They show rapid performance degradation, or sometimes their performance just deteriorates to zero at much shorter context lengths. For example, they mention Qwen 2.5 Instruct 1M, a model supposedly capable of 1 million tokens. Its accuracy apparently dropped to 0.00 at just 896K tokens in their tests.
Wow, so it didn't even reach its theoretical limit before failing completely.
Right, whereas MemAgent was still going strong at 3.5 million tokens. That near lossless extrapolation seems to be a key differentiator.
Okay, that makes sense. Now, did they check why it worked so well? Was it just the memory structure, or was the RL really necessary?
Yes, they did an ablation study. That's where you remove parts of the system to see what effect they have. And it revealed something critical. The memory mechanism itself definitely provides the structural support needed to handle the long context. It gives it the framework. But, and this is key, the reinforcement learning is absolutely essential for teaching the model how to actually use that memory properly. Without the RL training, the performance still declined significantly as context grew, even with the memory structure in place, just not quite as fast as having no memory at all.
So you need both,
Yeah.
the structure and the smarts from RL.
Exactly. And this also means, as they showed, that MemAgent maintains consistently high performance across lots of different types of tasks. It validates that the memory mechanism, trained with RL, effectively generalizes.
Right.
It's not just overfitting to one specific task format like QA, it learns a general skill of long context reasoning.
Okay, let's make this really concrete. Can we walk through an example? Seeing it in action might help make it stick. Imagine we ask MemAgent. The director of the romantic comedy Big Stone Gap is based in what? New York City.
Right. This is a good example because it's a two-hop question. The model needs to find the director, then find where she's based. It requires connecting dots. So the paper walks through how MemAgent 14b tackles this. Let's say in round 1, it processes the first chunk of text. Maybe in that chunk, it sees some information about, say, the Ghost production team, and notes they are based in New York City. Now, that's not the answer yet, but the model, using its learned strategy, intelligently chooses to retain this potentially useful info about NYC in its memory, just in case, like jotting down a possible clue.
Okay, so it holds on to things that seem relevant, even if not the direct answer.
Exactly. Then, maybe in round 2, the next chunk of text arrives, and perhaps there's nothing directly relevant to the question in it. No mention of the movie or director. What MemAgent does here is maintain its state. It doesn't get distracted or overwrite its useful NYC clue with irrelevant stuff. It shows robustness. The memory related to the question stays put.
Good. Doesn't get sidetracked easily.
Then finally, in round 3, the crucial information appears. Both relevant Wikipedia snippets pop up in the text chunk. It sees that Big Stone Gap was directed by Adriana Trigiani, and it also sees that Adriana Trigiani is based in Greenwich Village, New York City. The model correctly identifies these critical pieces of information, connects them to the NYC clue it already stored, and updates its memory accordingly. This leads it directly to the correct final answer. Greenwich Village, New York City. It successfully navigated the 2 hops.
And here's the really cool part, the aha moment, for me anyway. These intelligent memory behaviors, storing potential clues, ignoring distractions, making those multi-step connections, they aren't explicitly programmed rules, right?
Not at all.
They actually emerge as text generation abilities that have been reinforced through that RL training process.
Precisely. It literally learns how to be a smart note taker and a multi-step problem solver, all through optimizing for that final reward signal. It's emergent intelligence for memory management.
Wow, that's powerful stuff.
So yeah, wrapping up, what does this all mean? For you, the listener, maybe trying to learn complex topics, and certainly for the future of AI. Well, this MemAgent approach offers a really practical way to turn existing LLMs into incredibly efficient long-context reasoners. And with what seems like minimal engineering overhead compared to other methods, it effectively solves what the paper calls that long-context trilemma, getting arbitrary length, near lossless extrapolation, and linear cost. It feels like a genuine leap forward because it lets LLMs interact with information in a way that's fundamentally more intelligent, more scalable, and yeah, more human-like.
So thinking about that, if LLMs can now realistically process and intelligently summarize, entire libraries of information, how does this reshape the way you might access and synthesize knowledge in the future? What new possibilities does this open up for information discovery, for research, maybe just for understanding incredibly complex systems or histories? Could this be the key to AI assistants that can truly absorb your entire professional library? Or maybe even vast swaths of human knowledge and help you navigate it in totally new ways? What vast new documents are we going to task these models with next, now they might actually be able to read them?